国还是不能只考虑那个一个，
Okay, so now we go back to single phase. So if you have a charger to charge your cell phone, what do you need? Maybe you need 6 volt DC, right? But can you plug in this circuit and supply 110 volt directed to your cell phone? No, then you will burn out your cell phone. So what you need is 6 volt DC. How can you get 6 volt DC? You can say it is very easy. Maybe I can design full bridge rectifier. So we have AC input. And then we use a transformer. No, we use a filter. And then we design a DC to DC buck. Then we can get 6 volt. So first we design rectifier. Then we have a filter. And then we design DC to DC converter. Then we convert to 6 volt. So we have input. So this is our input. And here, if I do not use capacitor, then my output is like this. Right? My output is like this. So do you think this is DC voltage? Here we need DC voltage. Do you think this is DC voltage? It is DC voltage, but with a huge ripple. Right? So what should you do? You have to design a filter. What kind of device can you use for DC filter? Inductor, resistor, or capacitor? Which one? If you need a DC filter, do you need resistance or inductance or capacitor? Capacitor. So you use a huge capacitor, maybe 100 microfarad. So you use a huge capacitor. After you use the huge capacitor, it is like this. Oh, it becomes very smooth. However, the DC capacitor is very good for DC. But do you think the DC filter is good for AC? So we have to consider this one. So we have positive, negative here. So we go this way to charge the capacitor, and then we go back. So in this case, only this time interval, the input is larger than output, then the diode turn on. So the diode turn on only in this time interval. So if we check here, then the diode turn on in this time interval. Then we can get current, huge current. But after that, the input is smaller than output, then the current becomes 0, right? So what can I get? I can get the current like this. If I refer to the input, then I can see this is my voltage. This is my current. So my current is like this. So do you like this current? If you have this current, then what is the fundamental? The fundamental is like this. But do you think your current is very close to your fundamental? No. It is distorted. You say, then it doesn't bother me because what I need is charger, right? Why do I worry about input? Input is not my business. Input is Taipower company's business. I am a user. I only consider my computer and my cell phone. Why do I worry about the input current harmonics? And you say, I don't care, right? So what is this price? If you design this circuit, maybe it is easy. You can spend 500 NT. You can buy a very good charger. Then you are happy. But do you think the Taipower company happy? If you have a building, this building has 1,000 notebook, then what happened? You can see the whole building, the current become like this. They can disturb the utility, right? Because if only one ampere, I'm happy. But now it is 1,000 in this building. Then the current become 1,000 ampere harmonics flow to everywhere. Then Taipower company are not happy. They say the power quality is not good. The power quality is not good. So if you have a river, clean river, but there is a factory, chemical factory here, then they throw out waste material, then the water become red color. Do you like this? You say no. You pollute the environment. Then what happened? The government environmental bureau will come to check it and give a ticket to the factory. Say you have to punish 1 minute. And the boss say, oh, it is not good. I don't want to get a ticket, right? Then he asked the engineer to say, could you please solve this problem? And the engineer said, it is okay, but I need 1 billion. Do you think the boss will buy it? I can totally clean it, but I need 10 billion. Do you think the boss will buy it? They said no, then we will be bankrupt, right? What I want you to do is to pass. I don't want you to do perfect, right? So you have to pass the regulation, and tomorrow the government office come here, he check, he say pass, then I'm fine. But I don't need to, I don't want to pay 10 billion to improve it because I cannot afford it, right? So now the circuit create this current, and then what happened? You don't care. You say I still buy it, but then every country have regulation. They say if you create this kind of current, your charger cannot be sold in my country. So you cannot sell your product in our country due to the environmental issue, right? Then do you think your boss will be happy? They say, no, we need a market, right? So he call you and you say, okay, I'm fine, but I need this money to improve a new product. We have to sell a charger for this money. Do you think your boss will buy it? No, he said, tomorrow you want to come here. I don't want to see you again, right? Because it is impossible. So we have to compete with another supplier, right? So if original we save this money, what we can do is maybe 600 NT, right? So your boss tell you, I need a free lunch. So what is a free lunch? You need a good meal, but you don't want to pay. What can you do? Then you check email or some public announcement. If somebody passes the exam, then you say, oh, congratulations, this lunch you should pay for me, right? Then what do you get? Free lunch. So your boss also need free lunch. He say, I only can pay a little, but I need to pass, right? So if you design a PFC, you have to keep in mind, you don't need to do perfect. It is not like DC converter, it is not like inverter, because inverter, people need performance. Converter, people need performance. But PFC, people don't care. Who cares? Only government. So if I can pass, then I'm fine. So I don't need to get 100%. Okay. So this is the fundamental idea. So if you design PFC, you cannot use a very complicated circuit. You have to use as simple as possible circuit. But what you need is pass the regulation. So this is the general idea. So now you cannot pass. So what can you do? So you have to go back to think. And then you tell your boss, I don't have any idea. Then your boss say, next week, you don't need to come to see me, right? Because this is your job. You are engineer. I'm not an engineer, right? So he asks you to finish this assignment in 1 week. So we can see, we learn that if you use rectifier, then only here the current flow. Then the current is discontinuous. If the current is discontinuous, it is far away from sinusoid. Then your harmonics is huge. Your power factor is poor. So you can say the current has a huge distortion. Too much distortion. However, everybody loves it because it is cheap. So for users, they don't care because they only need to charge. The power quality is not user's business. It is government business. It is high power companies' business, not users' business. However, now many countries set some regulation. They say if you sell computer, if you sell charger, you have to get 0.9 power factor. The total harmonic distortion should be less than 5%. If you cannot pass, you cannot sell. So then you still have to solve this kind of problem. So how can we solve this problem? Then you go back and sleep. After 1 week, you have idea. Can I replace the capacitor to inductor? Right? Very simple, right? So I use inductor, large inductor here. So if we turn on the diode, then inductor create constant current, right? Inductor create constant current. Then what happens? Then we have a circuit. If we put huge inductor, then the output becomes constant current. So like this. So if I turn on D1 and D2, so we have AC source here. Then what happens? Then we can go here, and go here, and go back here. Then we can get 1 ampere. So here we can get 1 ampere. We have current 1 ampere. If D3 and D4 turn on, then we can go this way, and then we go this way, and then we go to this way. So we reverse, so we can get minus 1 ampere. So we change the current into square wave, right? And if we have 1 ampere here, then the fundamental is here. And we can calculate the square wave is very close to the fundamental. So what is your power factor? So we can calculate the power factor. And what is your phase? The phase is perfect, 0, 0. So the phase shift is 0. Cosine 0 is 1. So what is the power factor? The power factor is distortion factor multiplied by displacement factor. So distortion multiplied by displacement. Now the current and the voltage are in phase. So cosine 0 become 1. This is 1. Perfect. The only is distortion, right? So the square wave is very close to sine wave. The distortion is small. So we can calculate the power factor 0.9. Do you think 0.9 is good enough? Yes. Then you pass. Then next week you feel very happy. You go back to see your boss. Say, I got one idea. It is very simple. Before we use huge capacitor. Now we can remove huge capacitor. We use huge inductor. Then everything is fine. It is true. Then you pass. But what is the disadvantage? If you need huge inductor, how about the space? You have no space, right? How about the cost? Huge cost. How about the weight? Huge weight. So do you like to bring 5 kilogram computer every day? No, you say, I don't want to buy it. So the idea is good, but it is not feasible. So because it is too huge, the weight is too heavy, the cost is too high, the size is too large. Then your boss say you are an engineer, you only consider your own side, right? But you do not consider customer side. So this idea is okay, but not feasible. You have to go back to think another idea. Otherwise, you don't need to come here again, right? Because it is your responsibility. Then you say, my professor didn't teach me that. It is his fault, not my fault. But your boss say, it is your own business. I don't care about your professor, right? So it is still your job. So how can you solve this problem? So you can see this is not feasible. We can use some calculation. We can calculate power factor. It is kilowatt divided by kVA. So this is power, this is kVA, and finally we can get a 0.9. But it is too heavy and the cost is too high. So we can use Fourier series to analyze, and we can calculate. It is true. Finally, the power factor is 0.9. But this idea is not good. So we have to solve another way. So how can we improve the power factor? It become a new trend. A new trend. So if you work for a subway system or MRT, and then everything is fine, the car is fine, the railroad is fine, but finally, Thai Power Company say I cannot supply the electricity to MRT system. The reason is you use AC to DC, and the power factor is too poor. Then I cannot supply electricity for you. So everything is ready, but the power quality is not good. Then what can you do? You have to wait. Then your boss will call you again. You have to solve the problem in 1 week, right? And you say, I have no idea. So for this kind of system, power system, for steel company, what is the current? The current is 1,000 ampere. What? 1,000 ampere or 2,000 ampere. So can I use device, IGBT, MOSFET for 2,000 ampere? No. There is no this kind of device. So it become a challenge. It become a challenge. So finally, there is one company, ABB. It is Europe company. They do research on this issue. So they develop what we call multi-pulse method. Multi-pulse method or multi-pulse converter. They say we cannot use device. We have to use another way. What can we use? We can use inductor. We can use transformer. So they use inductor. They use transformer. Do you think an inductor or transformer is passive or active? What is active device? Switch, active, right? But how about inductor? Passive. So they call this is passive PFC. So they spend a lot of effort to do research, and they found the solution, and then they apply for patent. And if you use this, you have to pay the patent fee. You cannot just use it. So it already registered by ABB. So ABB put a lot of efforts to study this kind of issue. They say, if I can use transformer, this is delta, this is delta. I use another transformer, this is delta, this is Y. And I use two transformer parallel to share the load. For example, you have 100 kilowatt, but here 50 kilowatt, here 50 kilowatt, total 100 kilowatt. Then it is okay, 50%, 50%. Then what happens? If I use delta to delta, I can show the input current is square wave. It is like this. It is like this. If I use this one is delta, this is Y, then I can get the waveform should be like this. So from the electrical machine, you can prove this. If you learn transformer, you can prove this. Then we use Fourier series. This is I1. I1 is fundamental. 5 harmonics, 7 harmonics, 11 harmonics. This is minus, plus, minus. You ask, how about the third harmonics? Third harmonics cancel each other. So didn't appear, right? So this is I1. How about I2? If you put delta to delta, it is like this. Cosine, this is 5 harmonics, this is 7 harmonics, this is 11 harmonics. So the amplitude is the same, but the sign is different. So if I put this one delta Y, this one delta delta, how about this current? It is I1 plus I2, right? So I1 plus I2, then fundamental become twice. 5th harmonics one is minus, one is plus, become 0. Cancel each other. How about 7 harmonics? One is plus, one is minus, cancel each other, 0. Then the fourth one become 11 harmonics. So what is the amplitude? 9%. So you can see before, one is the harmonics. We have fundamental here, and then we have fifth harmonics, 20%. This is the fifth harmonics. We have 7 harmonics, 40%. Then we have 11 harmonics, 9%. 9%. This is 7. This is 40%. 9. This is 11. 9%. So if I put this one 20%, this one 40%, then total could be 40%. So these two become 40%. But now we can cancel this one, the fourth one become 9%. Do you think it improves? Yes, it improves a lot. So the idea is quite smart. So then ABB get a lot of money, a lot of intelligent property. If you want to do this, you have to apply for the patent. You have to get the permission from ABB. Then ABB charge you. So we can see this is good idea. But this idea is good, but not perfect. If I have 2 trains, how can you make sure one train is come here, another train is go back? So now you have Gongguan and the Taipao company. So you have this one. If you want to balance, one train should go here, another train should go here, right? Then 50%, 50%. But sometimes 2 trains go here, no train go here. Then still unbalanced. So how can you make sure this load is equal to this load? You can say, I don't know. Because if you have high-speed train, if you have MRT system, how can you guarantee this load and this load always equal? I cannot guarantee, right? Then this technology become useless because not automatically share 50%. Then your advice discuss with you and then say this has a disadvantage. Can you solve the problem? So you have to go back, right, to sleep and to propose idea. What can you do? Then some people go back and sleep, and finally they can propose new idea. The idea is like this. Because the load is random, is not guaranteed. So now we put load together. So this is load 1, this is load 2. Then if you have 2 loads, then this voltage and this voltage cannot be totally the same. Sometimes they have different, especially when you use SCR. So they use inductor to avoid the inner loop current become too huge. So they use inductor to limit the circulate current. Right? So if you have a battery here, another battery here, you want 2 batteries parallel together to supply the power, but then the battery could go here, right? This is 5.1, this is 4.9, right? 5.1 minus 4.9, this is 0 resistance, then become infinity current. So most current go here. Then you burn out 2 batteries, right? So you can try. You can go to 7-Eleven, buy 2 batteries, tie together. Then what happens? Burn out 2 batteries. Because the inner resistance is not equal, right? Inner voltage is not equal. So if you have two voltage, can you tie two voltage parallel? No. You will burn the two voltage source immediately. So what should you do? You have to put some resistance between them, right? To limit the current. Now we put the inductance to limit the current. And then this is DC. So we hope half power come from here, half power come from here. So we have together power 100 kilowatt. And then we use the inductor to limit the inner current. Then we put all money together, and then we supply the power to here and here, become one set. So you have brother, and you put your brother's money and your money into bank, and then if you need the money, you just draw from the bank. Then your property is equal to your brother's property, right? Because you have a common bank. So now we put a huge bank, and if you need a load, you just supply load. Then we can guarantee this one and this one almost equal. Then no problem. So this is the improvement of the previous. This one supply this one supply this one, but the load could be different. But now we use the whole system to supply these two. Then each one share almost 50%. Then it is work very well. So ABB provided this idea, and they get a lot of money. So what is the result? If you have this current and this current, now from here is I1 plus I2 become this current. Do you think this is close to sinusoidal? Do you think this is close to sinusoidal? Do you think which one is more close to sinusoidal? Which one? This one. Why? 1, 2, 3, 4, 5, 6. So we call 6%. So we call this is multi-pulses. The more pulses, the more opportunity to close sinusoid. So if you only use this one, then you have fifth harmonics, 7 harmonics. If you use this one, you have fifth harmonics, 7 harmonics. But this one plus this one, fifth and 7 cancel each other. You become 11 harmonics and only 9%. It is here. So the idea is very clear and very clever. So do you have any difficulty to do this transformer? No problem. Delta to delta, delta to Y. Everybody can do it, right? You have transformer. You have A. You have B. You have C. We call this is Y. We have A. We have B. We have C. We call this is delta. So not special. So everybody can do this. So this is easy to implement. Then the ABB proposed another idea. He said if I can design a special transformer like this, like this, like this, then I have 3 transformers. This is second winding, second winding, second winding, and I have primary winding here. So primary winding is this current plus this current plus this current. Then I can get sinusoidal waveform. But the problem is I need 20-degree phase shift. So if you have a transformer, how can you design a transformer with 20-degree phase shift? You have a transformer here, A phase, here B phase, here C phase. So what is the phase shift? This is 120, right? 120, 120. So always 120. You also can put into delta. This is okay. So we call this is Y, this is delta. If we use 1 delta delta Y, then we can get previous result, right? But now APP say, oh, I need A phase, and here A phase should connect to B phase. So it is like this. I have transformer, this is A phase. I have another transformer, this is B phase. I have another transformer, this is C phase. So how can I design the transformer? First, I go to A phase and 100 turns. So I have 100 turns. And then I go to B prime. So I go to B phase. How many turns? Maybe 20 turns. So the transformer is not regular transformer. You have to write A and then go to B, and here you have to get C phase 100 turns, and then you have to go back to A, and here you use B phase, but you have go back to C. Then you have to the line come from here. So the transformer becomes special transformer. It is very hard to manufacture, right? Before, they just do this one, do this one, do this one, and then you can type by your own. But now you have to turn this one, go to here, and then you have line come from here. It is very complicated. How about another issue? If you need 20 degree, this is A phase, and this is B phase. And what do you need? You need 20 degree. So you need A phase and B phase come together. But you need this one and this one. This is 20 degree. So if this is 110, A phase is 110, and you calculate this one, it is 19.5 How can you design 19.5 tons? Half ton. How can you design this transformer? You cannot design, right? You can choose 90, you can choose 20, but then the angle is not 20. It could be 21 or only 19.5. So you can see this is a challenge. We cannot get perfect 20. So if here I get 20, here I get 0, here I get minus 20, then I can prove the input current is sinusoidal. But in the real world, it is very hard to implement this kind of transformer. So you can see this is one transformer, this is another transformer, this is another transformer, and we have main transformer here. They supply 1, 2, 3 load. So I line is equal to I1 plus I0 plus I1 minus. So the 3 current summation become this current. So the idea is very simple. We use synthesize method to create the current. And the current could be 1000 ampere, more than 1000 ampere. So we can see this one. This is the primary side. This is second side. So I need a regular transformer. But here, special transformer, advanced 20 degree. Special transformer, minus 20 degree. So we have 3 current. This one is I0, this is I plus, this is I minus, and then we use this current plus this current plus this current become primary, become this current. So it is beautiful, right? So then we can solve the problem. So this is 18 Perth. 18 Perth. So this is provided by ABB. Also, they propose this idea. We have Y connect, but here we use this kind of transformer. Here, maybe 50-10, 50-10, 50-10, 50-10, 50-10, 50-10, but the output comes from middle. So this is 12 Perth converter. So then we can get the current closer to sinusoidal. So the current is like here. So we have I4, I5, I6, I7, I8, I9. So we get this current. So if you propose this idea, what can you get? You get a PhD for tomorrow. What can you get? A patent. Next week, what can you get? A job. Next year, what do you get? A good future, right? So what do you need? You need to calm down and to think. So you have to propose this kind of new idea. So this is well put. So if you are interested in this topic, then you can use the keyword multi-pulse method for clean power. So if you use multi-pulse method, what do you mean? You use transformer, right? You use transformer. You design special transformer to create different pulse. And then in the primary, you add different pulse to create sinusoidal. And this kind of technique can be used for high power, 1,000 ampere, 5,000 ampere, for high-speed train, for power system, for HVDC, something like this. But for the computer, for the cell phone in general, we use active power factor correction. We use MOS, we use IGBT, we do not use transformer. The reason is it is too complicated, and the performance is not perfect, still have some harmonics. So we call this is power electronics converter harmonics, and this is one book. And if you are interested in this field, you can get this book to study it. Now we go back to active power factor correction. So what is active power factor correction? So we have sinusoidal input, we have full bridge rectifier, and then we have DC-DC converter. So what is DC-DC converter? Which means change the voltage. So in our brain, we can think, if you want to change the voltage, it is like a transformer, right? Transformer can change voltage. So here, we use transformer to represent the changing voltage. And then we can use a capacitor to make a filter and then load. So in this case, we need what? If you need a PFC, you need rectifier, but you also need another thing. What do you need? Converter. And this converter is boost converter. You have to design boost converter. You cannot design buck converter. And you may ask why, then we will explain later. So only boost converter. Then you can control the duty, you can control the controller. Then you can get sinusoidal voltage and the sinusoidal current. So what is the disadvantage for this idea? What is the disadvantage? What do I need? I need 5 volt. So I only need a charger 5 volt. So output is 5 volt. So I need a charger 5 volt. This is my cell phone. But now, what do I need? I need a rectifier So input is 110. Then after that is 145. I have 145 DC here. Then I need a boost converter. So what is boost converter? Means output is larger than input, right? Buck is output is lower than input. But now input is 154. How about output? More than 154, right? Maybe 400. Because output is larger than input. Then what is my output? Output is 5 volt. So I need a DC, DC. And then I need a 5 volt. And my load is here. So what I need is only 5 volt. Why do you change 154 into 400 and then go back to 5? Do you think it is reasonable? No, it is not reasonable, right? If I need a 4, I should change it 145 to 4 to 5. But then you cannot do PFC. So if you need PFC, what do you need? Boost and then buck. So then you waste your energy, right? And another problem is 5 volt, 400 to 5 volt. How can you control? Only maybe 1.52% turn on. Then 98.7 turn off, right? So the duty is so small. Turn on duty is so small. Do you think this is easy to design for 400 volt become 5 volt? It is very challenging because duty is too short, right? So you can see, do you like this topology? No, I don't like this topology. But why do you use? The reason is PFC need boost converter. So the only way is boost and then buck. But boost 2 times, then buck become 1%, 2%. So it is not good. Can you change this topology? Yes, you can change. Then you can graduate soon, because no one can do this. So from the basic principle, no one can disobey this rule. Otherwise, you cannot do PFC. So this is the challenge. You can see everybody knows this is not good, but we have no choice. And somebody say, oh, how many stages do you use? You use 2 stages. One is boost, and another is buck. So how many stages? 2. Can we use 1 stage? So we need AC, then DC, then I hope 1 stage, 5 volt, so 1 stage. This stage include PFC plus buck. So I need to put PFC and buck in 1 stage. Is it possible? So many students try to do this research. So if you go to IEEE, you can key in single stage PFC. Then you can get a part of paper. They try to propose this idea. Because from physical point of view, we can use 1 stage, right? But why we cannot do this? Because this converter has a mission to do regulation 5 volt. So its mission is 5 volt. How about this converter? This converter is PFC. So now, can I give a lecture here and make a phone call together? Because I'm only one person. I only can do one thing, right? at one time. But if you have a circuit, can your circuit can serve for PFC and a buck together? Very hard. If you do this, which means your performance is bad. If I give a lecture, but I also make a phone call, then my performance will become bad because I cannot focus, right? So this is the centimeter. So if you have no idea what is your topic, maybe I suggest you can do single phase PFC. It is a challenge because you have to do two things in one time, and these two things are conflict. The DC converter focus on regulation, output voltage regulation. The PFC focus on input current. But now you only have one converter. You have to care two things. Then how can you do this? You can say, I can pay half time for PFC, half time for regulation. Then it is a good idea, right? So we have many papers focused on this issue. So I think I can stop here, and I will see you next week. And after next week, we will have a midterm exam. I think it is April 13. Okay, see you next week.